So thank you very much for being here. It's a real honor to be able to be here to present some of my work to you. And I'd like to say thank you to Jean-Jacques and to the Collège de France for organizing and for giving the opportunity to be here to commemorate such an inspiring scientist as Yves Coppon. So I'd like to talk to you today about Australopithecus sediba, and I'd like to talk to you in particular about some of about the hypothesis that this species could be the ancestor of the genus Homo. And in particular, I work on teeth primarily, so I'm going to be giving you a dental perspective on this issue. So Australopithecus sediba was first, or fossils of sediba were first discovered in 2008 in Malapa Cave in South Africa. Malapa Cave, you can see, we won't point. You can see here on the map, it's in an area in South Africa which is very rich with very important hominin fossil sites, so sites such as Sterkfontein and Swartkrans and many, many others are all in quite a small area, quite nearby. And in particular, there are a number of fossil remains discovered, but in particular, we have these two quite remarkable partial skeletons that were recovered. They're remarkable both in terms of the preservation of the bones themselves, but also in terms of the completeness of the skeletons. So it's really rare for us to find skeletons that cover this much of the body, of the bones that we would be interested in studying. So firstly, we have, I'm going to try and point again. No. Firstly, we have MH1 on the left, which is a juvenile individual and is presumed to be a male. And then we have MH2 on the right, which is an adult individual and is presumed to be a female. We also have a number of additional isolated remains, but most of what we're interested in today, we're going to be talking about, is from these two individuals. And these fossils are dated to around 2 million years ago. And as you might have seen from the title of my talk, I'm particularly interested in how sediba is related to other hominins. And I just wanted to take a second to talk about why we're interested in this in particular. So over the years, and particularly in recent decades, we've been able to recognize an increasing number of species within the hominin fossil record. And as we do so, it becomes increasingly important for us to understand how these species are related to one another. And it's particularly important when we're discussing the evolution of certain complex features or behaviors. So maybe we'll be talking about the evolution of bipedalism or the evolution of a large and complex brain or the making and use of stone tools. In each of these cases, the evidence that we have available to us is spread over a large area in lots of different sites from lots of different time periods, and it can be associated with a number of different species. And so the challenge is to link all of this evidence together in order to build a cohesive picture of what was going on. And one part of that linking everything together is having a solid taxonomic framework, a solid understanding of how different species are related to one another. And this is particularly interesting in the case of Australopithecus sediba, in a way that was quite well summed up by the title of the paper initially describing the fossils. And in particular, we're interested in this part here, which is Homo-like and Australopith. So in some ways, this immediately raises some questions, and we have to understand what the evidence is for each of these components. So we're going to start with the Australopith part. We're going to start with the general features of the sediba skeleton that look Australopithecus-like. And there's a number of features that we can look at, but in particular, we have a relatively small cranial capacity, quite a small brain size, which is typical of Australopithecus. We can see here, we've got MH1 on the left, MH2 on the right, and we're comparing with Lucy, the skeleton that we've talked a lot about over the last 2 days. So we have quite a small cranial capacity. We have arms which are relatively very long relative to the legs, and we have an overall small body size. So you can see here sediba compared to a modern human, and so we have quite a short stature which is estimated for adults as somewhere between 130 and 155 centimeters. And we have quite a low body mass. So these in general are a few kind of general Australopithecus features. But we also, in addition to this, have a number of features that really distinguish Australopithecus sediba, not just from other Australopiths, but in a lot of cases from all other known hominins. So we have a really distinctive combination of features in the skull, and in the jaw, and in the foot and the ankle, as well as in the hand. So you can see here we have this beautifully preserved hand, and it has an overall morphology which is not matched by any other hominin we know. And in particular, we have a thumb which is extremely long relative to the fingers. And so these features are features which contribute to our understanding that this really represents a distinct species, that this can't be accommodated within the range of any species that we already know of. But we want to go further than this, and we want to know, even if once we've decided that this represents a distinct species, we want to know how it's related to the other species that we already recognize. And there are a number of ways in which Sediba is quite similar to another species, Australopithecus africanus. And africanus is known from a number of the cave sites in South Africa, which are relatively nearby, but earlier in time. And so a possible way of viewing Sediba then is a kind of late surviving relative of Australopithecus africanus. But as you remember from earlier, we also have this second part of the title to deal with, which is Homo-like. And so there are a number of aspects, particularly of the cranial morphology of Australopithecus sediba, which are suggested to resemble Homo. And in particular, the authors of the who described the fossils in the first instance said that the same features which can be used to distinguish Sediba from Africanus are those that align it with the genus Homo. And they went on to suggest potentially that Sediba could be the ancestor of the genus Homo. But we have an issue sort of immediately to deal with this suggestion, which is quite simply a time problem. So as you remember from the start, I said that the Sediba fossils are dated to around 2 million years. However, we have a number of fossils attributed to the genus Homo, which are older than 2 million years. And in fact, the oldest of these is around 2.8 million years old. And so then it stands to reason that these fossils from Malapa cannot be the ancestors of fossils that are older than them. So instead, in order for this suggestion to work, we would have to hypothesize that there is a lineage of Sediba fossils for which we don't have evidence currently, which stretches back a long way into the past, beyond what we already have. And this lineage would have to be at least 800,000 years old. And actually, probability modeling of this scenario has found that it is quite statistically unlikely for this to be the case. However, we should still assess this claim on the basis of the morphological evidence. And yeah, so we have a number of features, particularly of the skull, to look at. And so a couple of them we can see here. So we can see in Australopithecus africanus on the bottom here, we have quite flaring cheekbones. So you can see marked by the dotted line here, which in Sediba are relatively reduced. And this is suggested to be similar to a number of early Homo specimens. And similarly, when we look at the skull from the top, we can see, there we are, I've worked out where the pointer is now. We can see we have this region behind the orbits, behind the eye sockets, which is relatively constricted in this Africanus individual, but is much wider in Sediba. And again, this is suggested to be similar to early Homo. However, we have to remember where this evidence comes from, and if I refer you back to our two partial skeletons, you'll notice that the second individual, MH2, the adult, doesn't have a cranium, doesn't have a skull or a face preserved. The skull and face that we're working off is that of MH1, which is a juvenile individual. And so it's been suggested that actually a number of the features that look Homo-like in the Sediba in the Sediba face and the Sediba cranium are those that would have changed as this individual grew. And so the skull and the face have not finished growing at the age that this individual reached. And there's quite good evidence that several of these features would have looked less Homo-like in older age. So what we really need to further assess these claims is a form of evidence that is more stable over different ages. And teeth are very useful in studies of hominin taxonomy in any case. They're very character-rich structures, and they're very well preserved in the fossil record, which simply means that we have quite a lot of them, and they preserve quite well. But importantly, in our case, teeth are not remodeled throughout an individual's lifetime. So they finish growing quite early on at quite a young age, and from that point on, their morphology is only altered by external factors such as breakage or wear or disease, which tend to be a bit more predictable. So this is very useful in this case because it means that in MH1 as well as in MH2, we can discount the fact that the MH1 individual is a juvenile, and we can compare its morphology to the other fossils that we have available to us. It's also possible to gain more information about teeth from the use of micro-CT scanning, which an example of which you can see here. So this is the MH1 mandible that we were just looking at. It's a CT-based reconstruction. And you can see from the external surface that we have the first and second molars here, and you can also see a little bit of the third molar there, just yet to erupt. And what we can do with CT scanning is we can essentially digitally extract this tooth, and it allows us to study it for, to gain more morphological information from this tooth. In addition to this, we can also study the internal structure of these teeth. So one particular thing that we might be interested in is looking at what's called the enamel-dentin junction, which is the surface that underlies the enamel surface of the teeth. And so what we can do with CT scanning is we can digitally remove the enamel cap of these teeth and reveal the enamel-dentin junction. And this is useful for us because many of the morphological features that we might be interested in at the enamel are also present at the enamel-dentin junction. And it means we can study them in slightly worn teeth. So you can see, for example, here in the first molar, we have a certain degree of tooth wear which might have removed some of the features that we might be interested in. However, they are preserved at the enamel-dentin junction. And just as a quick look of how we do this, this is a CT scan of a hominin premolar, and it enables us to digitally segment the different tissue types, the enamel and the dentin, and we can use this to build a 3D model of the tooth, which we can then manipulate in various ways, including to remove the enamel cap and study the enamel-dentin junction. So this is useful for us in a number of ways. The first one is, I'm going to give you an example of a feature that we might be interested in hominin teeth. So hominin teeth have a number of different cusps, and there are main cusps and what we call accessory cusps. And accessory cusps are much more variable. They're present in some individuals and not in others. You can see an accessory cusp here at the enamel surface, but you can also see it here at the enamel-dentin junction. So this is really useful for us because it means in the case of worn teeth, if the enamel is worn down to the point where we cannot assess the presence or absence of these accessory cusps, we can use the enamel-dentin junction to assess them. And this is particularly important because the presence or absence of these cusps have species-specific frequencies in some cases. So in this case, we're looking at a cusp on the lingual side of the first molar. So the lingual side means the tongue side. And we know from previous research, and we also know from some research that I've done at the enamel-dentin junction, that this cusp is much more common in individuals, in Homo individuals, than it is in Australopithecus individuals. And if you remember, this first molar here is somewhat worn at the enamel surface, which can make it a bit more difficult to assess whether or not this cusp was present. However, at the enamel dentin junction, we can clearly see that no cusp was present here. So this isn't absolute evidence that this tooth was or wasn't Homo or Australopithecus, and we can see that there are a number of individuals of Homo that don't have this cusp. But it is more typical, especially combined with the evidence of other accessory cusps within the dentition, it is more typical of the configuration that we would see in Australopithecus. We can also look at the overall shape of the enamel dentin junction, and this carries quite a strong taxonomic signal. In this case, we're looking at the second molar, again from MH1. The MH2 teeth are a little bit more worn in this case, which makes them more difficult to include. However, what we have here is a plot that's showing us certain aspects of the shape of the tooth, which differentiate between the genuses Australopithecus, Homo, and Paranthropus. And we can see quite clearly here that the shape of the M2 and several other teeth that we've analyzed as well is very typical of what we see in Australopithecus. So this is another line of evidence that we can use. The third thing we can do is we can look at the size of the teeth. And this is something that was particularly interesting in Sediba. They were already, it was already suggested that the teeth were quite small. But what we can do is we can look you can use these figures to look at the tooth size across the dentition. So we have here the comparative sample for Australopithecus, and we've got a measure of size along this axis here, and then we have each tooth position going from the front to the back of the jaw. And you can see the tooth size patterns in Australopithecus here. So when we add Sediba in, you can see that Australopithecus sediba either occupies the kind of lower end of the Australopithecus range for the molars, or for the more anterior teeth, it's actually below the range of what we see in Australopithecus. And if we limit this to just a comparison with Australopithecus africanus, then it's even clearer that these teeth are quite small. So you can see even some of the molars in this case are below the range of africanus. When we compare instead to early Homo, we see that early Homo generally has smaller teeth than Australopithecus, and so the molars are within the early Homo range. However, some of the anterior teeth, particularly for MH2, are below even the early Homo range of variation. And so, to conclude, the evidence from the teeth suggests to us that it really seems to be an absence of features which would suggest an attribution to Homo or suggest some kind of link with the genus Homo. We don't find Homo-like features in these teeth at the EDJ. The shape of the EDJ in general is very similar to what we see in Australopithecus, although there are some teeth where this is slightly different. And the final part of the picture is that the teeth are very small. So it seems overall that these are teeth that look very much like Australopithecus, but are slightly reduced in size. And in terms of putting this in perspective with the overall question, I would say the dental evidence doesn't provide very good support for a link between Australopithecus sediba and the genus Homo. So I'd just like to say thank you for listening, and thank you to all of the collaborators and institutions that have made this possible. Thank you.